Hi, Dr. Sanjay.
I'll be back. Okay, hi everyone. So this is ECE840, one of the 3 or 4 core courses that you'll have to take for your grad, whatever program you're in, master's or PhD. And then in this course, what we shall do is, as you have, if you have seen the course contents, which is available in the course website, then you'll see that we have 2 different sections in the blocks in this course, Block A and Block B, if you have seen this. So Block A will be linear algebra, advanced linear algebra actually, and Block B will be convex optimization. And both sets of topics are very important for almost any research that you wish to undertake for your thesis or your dissertation, or even otherwise, it's one of the core requirements, and you'll learn a lot of mathematical tools in this course. Now, this course is not specifically focused at any single application. Okay, so these are tools that you can use, mathematical numerical tools that you can use in any application, very useful tools. And I will also provide some illustrative applications as examples. I expect that you guys would be familiar with MATLAB programming. So anyway, so you saw this is the course objective, and so these are the outcomes. You can give it a read. And instead of this short syllabus, you have the whole schedule of lectures in front of you, which you can use. Now, this is the background that you need for this course. Make sure that you understand vectors and matrices, determinants, rank, the inverse of a matrix. And by that, I mean you will be able to find the rank of a matrix or hand calculate the inverse of a matrix, and that you understand linear equations in vector matrix form. And you should also be familiar with MATLAB programming, not just typing a simple code, simple commands in MATLAB, but actually writing MATLAB code. If not, then you really should try to hurry up and learn MATLAB yourself. I strongly advise you to do so. But officially, the prereq is 540, where you do MATLAB, and basically you do all these things in 540. So the prereq is 540 or equivalent. Now, there are tons of books and lecture notes available online, but I will be providing enough material through my own lecture notes and the slides. So there's no formal textbook requirement for this course. Now, one request for all of you is don't send me emails pertaining to this course via webmail. Okay, always use Canvas email. But first, if it's a generic question, then post it in the discussion board so that I can share it with everyone. Okay, step 1, if it's a generic question, then you should first try to post it in the course Canvas message board, so that when I respond, others can also view it. And furthermore, others can reply to it if I haven't seen your question. Or if you have any other observations about this course, you're free to use the message board. That's the first step. Now, if it's of more personal nature that you don't want to share with others, then you send me an email via this Canvas email, but don't use webmail. Okay, that's my request. If you want a prompt reply. then use Canvas email. And anyway, this is online, everything is online. So a lot of these things don't apply to UNIST exams. And well, academic honesty is something that you should read, and do read everything here. And one more thing, these topics are almost certain I'll be covering these topics in this specific sequence. Here, 3 slots are TBD, that is to be decided. I'll look at, when we are doing this course, I'll look at what your interests are, what your background is, and so on, and accordingly, I'll fill in these 3 slots. But that's towards the end of this course, so you shouldn't have a problem. We all know what we're going to learn almost until the middle of April. Now, suppose we have to cancel a lecture because of, for some reason, some software issue, or because some emergency on my side. In that case, we'll move all the lectures by 1 time slot. Okay, suppose February 23, for instance, you're not able to do lecture A7, then we'll do lecture A7 on February 25 and A8 on March 2, and so on. Everything shifts 1 row down. That's why I have this extra slot in each case. Okay. So now let's begin with the review of vectors and matrices. So let me go to that slide here. Okay, so here we are. Review of vectors and matrices. Now, these are what we shall do. Now, since this is a review, I'm skipping some very basic rudimentary topics in vectors and matrices. Let me just take a 2-minute break. I'll be right back. If you have any questions or if you want to discuss something, then feel free to do so. But meanwhile, let me show you this entire screen so that you'll be able to see something at least. Okay, so inverse of a square matrix. Square matrix may or may not have an inverse, okay? If it's a singular matrix, then it doesn't have an inverse. Otherwise, the inverse of the matrix A is A inverse, and A inverse A and A inverse both are equal to the identity matrix I. Okay, what's an identity matrix? All the non-diagonal elements are zeros, and the diagonal elements of the matrix, identity matrix, is 1. AB inverse equals B inverse A inverse. Okay, remember this. The matrices A and B change positions. AB inverse is B inverse A inverse, not AB. It's not A inverse B inverse, okay? Now, determinant of a square matrix, now you know what determinant is. Now, determinant of the product AB of 2 matrices, we use both notations, det AB and this within these kind of brackets, AB, both to denote the determinant. And this is equal to determinant of A times the determinant of B. The determinant of the product of 2 matrices is equal to the product of their determinants. the determinant of a transpose of a matrix is equal to the determinant of the matrix. Scalar multiplication is alpha is a scalar, and this A here is an n by n matrix, n as in New York. Okay, so if the size of this square matrix A is n, then determinant of A, alpha A is alpha to the n times A. Okay, so what's the determinant of negative A? It depends on whether it's an even size or an odd size matrix. Determinant of negative A will be determinant of A if it's a 2 by 2, 4 by 4, 6 by 6 matrix. If it's a 3 by 3 matrix, 5 by 5 matrix, etc., then determinant of negative A would be negative of determinant A. Okay, remember this. Determinant of A inverse is 1 over the determinant of A. And this is one expression that's very handy during some problem solving. Determinant of I plus AB transpose equals 1 plus A transpose B. Now, throughout this course, bold uppercase will always denote matrices. Bold lowercases will denote vectors. And by vectors, I will, by default, mean column vectors. Okay, if we want to represent a row vector, then I'll, in almost all cases, use B transpose to denote a row vector. I'll specifically have this transpose operation. Okay, and scalars will be italicized and not bolded. And they may be uppercase or lowercase. Okay, so block or bold uppercases, non-italicized are matrices. Bold lowercases, non-italicized are column vectors, and bold lowercases are non-italicized are vectors. And finally, italics, non-bolded, are scalars. Okay, throughout this course. Now, basic properties, conjugate transposition. The Hermitian of a matrix A is equal to A star transpose. So what you do is, star is the complex conjugate. So you take each element of the matrix and then take its complex conjugate, and then you swap the rows and columns. So that's transposition. That's a H, Hermitian of the matrix A. Okay, and except in rare circumstances, 99.9% of this course, we won't be using complex quantities. We'll focus on real numbers. Therefore, this H is the same as the transposition, because A star is equal to A if we are using only real quantities. Now, AB transpose equals B transpose A transpose. Just like the inverse, you have to swap the order of matrices. In a transposition tree, you have to swap the order. Now, for a Hermitian matrix A, the Hermitian is equal to the matrix A itself. Okay, now for real matrices, A transpose equals A. We then say that the matrix is symmetric. If A transpose is equal to A, then the matrix is symmetric. The trace of a matrix is the sum of its diagonal elements. Okay, so this is the AKK. So this is the row index K, this is the column index K. And AKK is one element of this matrix A. So we take the sum of the diagonal elements, that's the trace of the matrix. Now, some properties of the trace of a matrix. Trace of AB equals trace of BA. A and B are square matrices. A transpose A, if A is a column vector, A transpose A is equal to trace of AA transpose. Here's a pretty interesting formula that's proven to be handy in a lot of different derivations. Now, here's another formula called the Sherman-Morrison formula, and we'll do the derivation of this one. We'll see why this is true. If A is a matrix and B and C are vectors, now if B is a column vector, C transpose is a row vector, what happens? BC transpose becomes a matrix, right? So A is a matrix and BC are, I suppose they're of the same dimensions as the size of A, then BC transpose is another matrix which has the same dimensions as A. A is a square matrix. Okay, then A plus BC transpose inverse is equal to A inverse minus A inverse BC transpose A inverse over 1 plus C transpose A inverse B. Okay, now in general, you cannot have division by a matrix, right? But here in the denominator, this is the C transpose A inverse B is a scalar. Okay, and you can verify that. C transpose A inverse B will be a scalar. So this is a scalar quantity in the denominator. So this is true. Don't get confused. You cannot ever divide anything, a scalar, a vector, or a matrix with a something that's a vector or a matrix. The denominator has to be a scalar always. Okay, and you should be able to. You should know this. Okay, now let's do the proof of this. What we should do is we're trying to prove that the inverse of this is equal to this. So what if I multiply the right-hand side with A plus BC transpose? What should I get? The inverse of a matrix, when you multiply it with the matrix, what do you get? I, the identity matrix, correct? So if I do this multiplication, I should be able to get the identity matrix, right? Because this, the second factor here is the inverse of A plus BC transpose. So A plus BC transpose times A plus BC transpose inverse should be equal to I, the identity matrix, right? And so let's see if this product gives you the identity matrix. So what we do, the first step is we open up this second parenthesis. So A plus BC transpose A inverse minus A plus BC transpose times the whole thing. A inverse BC transpose A inverse over 1 plus C transpose A inverse B. Okay. Then what we do is we open up this parenthesis here. Okay. And here, I'll go to the next term here. First, this is AA inverse plus BC transpose A inverse, then minus. Here, I chose not to open up. Okay, what I've done is I've multiplied this and this. So I have, in the numerator, I have A plus BC transpose times A inverse BC transpose A inverse over the denominator. And now I open this parenthesis up. So AA inverse BC transpose A inverse, then plus BC transpose A inverse BC transpose A inverse. Okay, what's A inverse?
Identity.
Exactly. So this is the identity matrix. So, and what's A inverse here? This is the identity matrix, right? So what we get is this. What we get is I plus this whole thing, and this AA inverse I just did not write it here because it's the identity matrix here. Okay, so we have I here. So we have to now show that this term and this term cancel out. Okay, because we have to show that it's equal to I, right? So this is, what I do is this, I further uh, simplify like this. I see that B is on the left-hand side of both these terms. So I take B common, and then 1 plus C transpose A inverse B. And then on the right side, I take C transpose A inverse common. Now, what's in this parenthesis here is a scalar, right? C transpose A inverse B is a scalar, correct? 1 plus C transpose A inverse B is a scalar. Now, scalar, normally, you should never violate the order of multiplication. BC transpose A inverse is not the same thing as BA inverse C transpose, right? So you should always preserve the order in which the matrices or vectors appear in the each term. But except if it's a scalar. If it's a scalar, then you can put it anywhere. In fact, this is a scalar, so I can just put it here, right? Right at the beginning, and then BC transpose A inverse. Okay. That's what I do here. Since it is a scalar, I put it on the left. But I preserve the order of operations, order of appearances, excuse me, B, C transpose A inverse. This is B, C transpose A inverse here. Now what do you see? In the numerator, you have the scalar 1 plus C transpose A inverse B, and it's the same thing as the denominator, correct? So we can cancel them. What have we left? The third term is negative BC transpose A inverse, right? And so we have plus BC transpose A inverse minus BC transpose A inverse. That's equal to the identity matrix. These two cancel out. So this is I. We're left with I here. And so we just showed the Sherman-Morrison formula to be valid. Okay. Now, don't try to blindly solve it as if these are all scalars. Let's see what happens. Okay, so let's see. So we were here. This is one of the intermediate steps. And then I take BC transpose A inverse common. And then I write 1 plus BC transpose A inverse here. That's invalid. Why? If they were all scalars, this would be valid, right? But be very, very, very careful when we are dealing with vectors and matrices, because BC transpose A inverse, we take common. This side, if you put a 1 here, it's a scalar, but BC transpose A inverse is a matrix. The second term is a matrix. So this, you cannot have a scalar plus a matrix. Okay. So this is wrong. Are you guys with me?
Yeah.
Yeah.
Okay. So cannot factorize this way as 1 is a scalar plus BC transpose A inverse is a matrix. What we could have done is put an I here, identity matrix, because this is a square matrix, BC transpose A inverse, and so we can put an identity matrix here. Okay, if we were to factorize BC transpose A inverse, take it outside, then this would be I plus BC transpose A inverse. But that's a correct operation. But what happens? We cannot simplify it further, right? So even if this is valid, we won't get I so easily if we do it this way. But if you go back to the previous slide, what I did was I took B common on this side and C transpose A inverse common on the right side. And what I'm left here is a scalar, and that's equal to the denominator. And that's why I could cancel them out. Okay. Okay, so you have to do matrix manipulations in a more insightful manner. Any questions? Okay, now vector norms. LP norm of a vector. If I have a vector x, its scalar components are x1, x2, x3 until xn. The LP norm is defined as I take the absolute values of each scalar component and that to the power of p. x1 absolute value to the power of p plus x2 absolute value to the power of p. And all these elements, I do the same thing, and then I add them up all together and then take the pth root of that. That's the definition of the LP norm of a vector. The L1 norm is simply the sum of the absolute values of the each scalar element of the vector x. X infinity norm, what we do is we look at the absolute values of all the elements and pick the one with the highest value, numerical value. Okay, that's the infinity norm. And the 2 norm or Euclidean norm, L2 norm, is by default, that's the norm. Unless specified otherwise, we will assume that we are, if the P is not specified, then by default, it's the Euclidean norm. And that's equal to square root of x transpose x. It can be seen that for any P, the LP norm is always greater than or equal to 0. Now, LP norm of alpha times x is equal to absolute value of alpha times the LP norm of x. Triangle inequality. The LP norm of the sum of two vectors, x plus y, is less than or equal to the LP norm of x plus the LP norm of y. Okay, this is an illustration of the LP norms for p equals 1, 2, and infinite. Okay, now for p equals 1, okay, what do? We take the sum of the absolute values, right? This one. Now this red diamond here, it's a square, is the locus of all vectors with L1 norm equals 1. For instance, consider this vector 0, 1. Okay, this is x1, this is x2. Consider the vector x1 equals 0, x2 equals 1. Okay, it's vertical, right? What's the L1 norm? 1 plus 0, which is 1, right? What's the L1 norm of 0, 1? Excuse me, this was 0, 1, this is 1, 0. 1, 0 is this one. 1, 0 is a horizontal line from 0 to here, okay? And 1 plus 0, L1 norm is 1. Consider 0.5, 0.5, x1 equals 0.5, x2 equals 0.5. What's the L1 norm? 0.5 plus 0.5, right? So this point here, or this vector, the L1 norm is 1. Okay, so the L1 norm of all these points, each point, each vector connecting 0, this origin, to that point. Okay, so I'm using the words point and vector interchangeably. Everywhere in this red diamond, the L1 norm is 1. L2 norm equals 1 is, L2 norm is basically the length, right? So we are considering this, look at this green circle, everywhere here, every point, the L2 norm is equal to 1. It's a unit circle, right? With radius, it's a circle with radius 1. This is the infinity norm. What do we do for the infinity norm? We take the max of the absolute values, right? Consider this point here, 1, 1. What's the max of 1 and 1? 1, right? So L infinity norm of 1, 1 is 1. The same as the L infinity norm of 0, 1, which is the same as the L infinity norm of 1, 0. They're all 1. So everywhere in this blue square, the L infinity norm is 1. Okay? The inner product, the general notation is this. We use these brackets here, x comma y. And for actually everywhere in this course, this inner product will be x transpose y, or which will be the same as y transpose x. Both x and y are column vectors of the same size. Okay. And that's actually the dot product also. In physics, we call it the dot product. So if you have two vectors x and y, their dot product is x transpose y, which is y transpose x, which is in 2 or 3 dimensions, it's x dot y in physics, which is equal to the length of x times the length of y times the cosine of the angle between them, right? So this is the angle theta between the two vectors x and y. Projection of x onto y. This is the graphical illustration of the projection. It's x transpose y divided by length of y. What's y divided by length of y? It's a unit vector along this direction of y, correct? So x transpose times y divided by length of y is basically x transpose times cosine theta, x cosine theta. So this is x cosine theta in physics, in 2 or 3D, correct? But in general, for n dimensions, we say that the projection of this x onto y is x transpose y divided by L2 norm of y. Cauchy-Schwarz inequality, the norm of, actually this is valid for any LP norm, the norm of x transpose y is less than equal to norm of x times norm of y. Why so? Because we have, just look at this, x transpose y is actually norm of x, norm of y times cosine theta. So here you'll have cosine theta as a factor, correct? That's why this holds. Now, vector norms we covered. What about matrix norms? For matrix norms, a matrix norm can be defined this way. The LP norm of a matrix A is equal to this. This expression is more explanatory. So we take a vector x, and then, so AX is a vector, right? So LP norm of the vector AX divided by the LP norm of the vector x itself. And then for different values of x, we'll get different values of this ratio, right? And so we maximize with respect to x. And that gives us that's the definition of the LP norm of a matrix. Okay, that's why we say that the matrix norms are induced norms. Properties of matrix norms, they're always greater than or equal to 0, and scalar multiplication. These are all, we saw the same things for vectors. They hold for matrices too. Triangle inequality also holds for matrix norms. Holder inequality is L2 norm of the matrix is less than or equal to the square root of the product of the L1 norm and the L infinity norm of the matrix. Okay, now let's look at specifically what's the L1 norm of a matrix. The L1 norm of a matrix is the maximum absolute column sum. And the L infinity norm is the maximum absolute row sum. Okay, and this is an illustrative example. I know so far you haven't seen any examples because this is assumed to be a review, but I just added a small example here. Let's say we are given this matrix A. What's the L1 norm? It's the maximum absolute column sum. So we take the absolute value of each column. So let's look at first column, 2 plus 1 plus 2. Second column, 4 plus 1 plus 1. Third column, 3 plus 3 plus 1. Okay, so maximum of 2 plus 1 plus 2, 4 plus 2 plus 1, 3 plus 3 plus 1 is what? This is 2 plus 1 plus 2 is 5, this is 7, this is 7. So answer is 7. Infinity norm of A is, now this is the maximum absolute row sum. We look at the absolute sum of the absolute values of each row. 2 plus 4 plus 3, 1 plus 2 plus 3, 2 plus 1 plus 1. 2 plus 4 plus 3, 1 plus 2 plus 3, 2 plus 1 plus 1. So what does it give us? 2 plus 4 is 6 plus 3, 9. Actually, that's the highest. So we get infinite norm of A is 9. Frobenius norm of a matrix. What we do here is we pretend that it's a vector. Okay, we take all the elements Aij, take their absolute values and square them, add them up and take the square root. Okay, it's like as if A were a vector, then this would be the Euclidean norm. Here's an example. So this is a matrix, and so we take each element and then so this absolute value of Aij squared is the same thing as Aij star Aij, right? Aij complex conjugate times Aij. So 1 times 1, 1 plus j, what's the complex conjugate of that? 1 minus j. The product of 1 plus j and 1 minus j is 2. 2, 0, 1, and 1. So this one. So this is, oh, sorry, excuse me. Square this. So that's 4. 4, 0, 1, 1, and take the square root of that. You get 3. That's the Frobenius norm of this matrix A. And you can compute it this way too. Square root of the trace of AAH. This is the matrix A. This is the Hermitian of the matrix. So AAH, take the product, we get this, right? This is AAH. What's the trace? Add up the diagonal elements, 7 plus 2. How much is 7 plus 2? 9. Take the square root of that, we get 3, right? So this also, this expression here also gives us the Frobenius norm. Okay. Now, how to handle block matrices? Okay, I'll give you one illustrative example. Always when we do the multiplication, make sure that we are multiplying elements of the right sizes. Okay, so let's show that the product of these two block matrices is equal to this. What's a block matrix? Each component of this matrix is a smaller matrix. Okay, and make sure we can only represent a matrix as a block matrix if as long as the dimensions of each block make sure that they're compatible. Okay, and only then can we represent a bigger matrix in terms of blocks. Okay, so how do we show that the product of these two block matrices equals this block matrix here? For the most part, we can pretend that these are scalars, okay, except we have to pay attention to the order of the appearances of the matrices. So this is, we do the multiplication, this is AI plus 0, 0. A inverse plus 0 times this, which is 0. 0 times this is 0. So A inverse B. And then second row we have CI plus I0 is 0. So CI plus 0. CA inverse B plus I times D minus CA inverse B. A times I is the identity matrix, so that's A, and 0 we can drop, so this is A. A inverse equals I, so I times B is B plus 0, B. CI plus 0 is C, and this you can cancel out CA inverse B and negative CA inverse B here, we're left with. So this is an identity. As long as make sure that this block A here is invertible. It's non-singular. Okay. Invertible matrix and non-singular matrix mean the same thing. And just a question to refresh your memories. What if the determinant of a matrix is 0? Then the matrix is singular. It cannot be invertible. A inverse of such a matrix won't exist. Okay? Okay, now this is something nonlinear. Gradient of a multivariate function. We have some function which accepts vectors as arguments, okay? N-dimensional vectors as arguments, and then it produces a scalar. That's why we call it a multivariate function. It's a function of multiple single scalar variables, which is the same thing as the function of a vector. Okay, the gradient of del f of x is, and actually I have an example here, is also written in this form, and that's this. So we take the function, the derivative of the function with respect to x1, which is the first element of this vector x, that's this. Then this derivative of the function with respect to x2 all the way until derivative with respect to xn. That's the gradient. Okay, so the gradient will be a vector. Hessian. Hessian is like the second derivative. This is the definition of the Hessian of a matrix. And all of these are second derivatives with respect to all the scalar components of vector x. The second derivative, del square f over del x1 squared, del square f over x2 x1, all the way until del square f over del xn n1. And likewise, we go down the rows. The last row we have del square f over del x1, del xn. And the last element here is del square f over del xn squared. This is the definition of the Hessian of a multivariate function, del square f of x. Okay. Here's one important thing that you should always remember. F of x is this, half of summation ij qij xi xj. Sorry, this is xj here, this small typo. This is xj plus summation pi xi. Okay. Now we define this matrix Q here. And then, so the first term is half x transpose qx. And likewise, we take all the pi's and stack them up into a vector p. So the second term is p transpose x. Okay. Always check the dimensions. X transpose qx is a scalar. P transpose x is a scalar. Okay. The gradient of this is this. Del f of x, remember always this expression, okay? A derivative is half of q plus q transpose x for the first term, and the derivative of the second term is p. See, this p transpose becomes p here, okay? Now, I could have also written this p transpose x as x transpose p, because p transpose x is the same thing as x transpose p. Both are scalars, and the derivative of that is p. So this is the gradient. Specifically, what happens when Q is a symmetric matrix? For a symmetric matrix, Q transpose equals Q, right? So Q plus Q transpose becomes equal to 2Q. And for a symmetric matrix, so this term is simply equal to QX, if Q is a symmetric matrix, okay? And the expression for the Hessian is this, half Q plus Q transpose. Okay, here is what I just said. When Q is symmetric, Q equals Q transpose, then del f of x is Qx plus P. And del squared f of x is Q, because Q equals Q transpose. Here's an example. This is f of x is half x transpose. This is Q, this is x. And this is P transpose 3, 1, and this is x. And that, if you do this multiplication, it simplifies to this. Okay, now we'll find the gradient and the Hessian. Gradient is, what's the derivative with respect to x1 of this 2x1 plus, what's the derivative of this term with respect to x1? x2, right? x2. And for this, oh, this is, oh, this, when we differentiate this with respect to x1, this is 0. Derivative of this with respect to x1 is 3. And derivative of this with respect to x1 is 0. So we get this. Likewise, when you differentiate this with respect to x2, what happens? First term becomes 0, second term becomes x1, third term is 3x2, and then we have 0 for this, and then negative 1. Right? But you can use the expression that del f of x is. Now, note that this is a symmetric matrix. 2, 1, 1, 3. This Q here is a symmetric matrix, right? So you can just plug in the expression del f of x equals qx plus p, and this is what you get. Same thing. What's the second derivative? Again, you can verify that. You can check each of these. You'll get 2, 1, 1, 3, which is again this. Take all the second derivatives of this expression here and plug them at the right places. You get 2, 1, 1, 3, and it turns out to be the same thing as Q. Okay? Any questions? Any questions anyway? Okay, so let's begin. Let's end this lecture, and we'll meet on Thursday then.
Dr. Lance, since the lecture is finished, I have something which is not related to the lecture.
Something what?
Yeah, I just want to ask about the class time for this course.
Mm-hmm.
Like I have another. I told this before. I have another class which is starting exactly the same time, same day, Tuesday and Thursday, and starting 2:30 to 3:45. So I don't know if it's possible to change the time or something, or it's fixed the time for this class.
For this class, actually, because there will be a lot of other students who are not, they are working, and for other reasons, about 50% of the students are absent today, and I expect the same thing because they are all working.
Oh, so I'll have to drop the other class. Okay.
No, you don't. You don't have to drop. So
What can I do in this?
you can always take both courses as long as it's allowed by. I don't know about whether it's allowed to do that, but you can always, since this is online, so you can always view the lectures later on.
So for your class, there's no problem to view it later on, because the other class, he told me that it's mandatory to attend the session, the Zoom session.
No, it's not mandatory for this.
So I can just watch online later. Okay.
Yeah.
And if I have a question, I'll email you or something.
Post it on
Okay.
the message board.
Discussion. Okay.
Okay.
Okay. Perfect. Thank you so much.
Okay. So any other questions, or shall we quit?
No, thank you, Dr. Das.
Not on
Okay.
my side.
What's that?
Yeah, you see, not on my side. No questions.
Okay. So see you guys then.
All right. Thank you very much.
Bye.
Thank you. Bye.
Thank you, Dr. Das. Bye.
Bye.